How does a robot lawnmower avoid getting completely lost? After hundreds of turns across a yard with no driver, no steering wheel, and often no visible markers at all? Because mathematically, it probably should. Every turn introduces tiny positioning errors. Every wheel slip changes the calculation slightly. And over time, those errors can compound fast enough to completely destroy accurate navigation. Yet modern, robotic mowers can still move around complex yards, avoid obstacles, cover grass efficiently, and return to their charging docks automatically. And the engineering behind that is far more advanced than most people realize. Many robot mowers start with a buried boundary wire installed around the lawn perimeter. A low-voltage electrical signal continuously travels through the wire. This creates a detectable electromagnetic field around the edges of the yard. Inside the mower, induction sensors constantly measure that field strength. As the mower approaches the wire, the electromagnetic signal changes intensity. The onboard processor uses those changes to estimate distance from the boundary and calculate when to turn away. But the mower also needs to estimate where it is everywhere else in the yard. That begins with wheel encoder sensors. These sensors track how many times each wheel rotates. By comparing left and right wheel movement, the mower estimates speed, distance traveled, and turning angle. This process is called dead reckoning. But dead reckoning has a major weakness. Tiny errors constantly accumulate. A slight wheel slip on wet grass, bump in the lawn, or uneven traction during a turn can slowly push the mower farther away from its estimated position, which means the robot continuously needs ways to correct itself. And this is where modern robotic mowers become surprisingly sophisticated. Some now use RTK GPS systems. Traditional GPS can be inaccurate by several meters. RTK GPS instead compares satellite signals with a nearby reference station, reducing positioning errors down to only a few centimeters. Other models use LIDAR sensors. LIDAR rapidly fires invisible laser pulses outward thousands of times every second. By measuring how long those reflections take to return, the mower builds a simplified three-dimensional map of nearby objects and boundaries. And all of this happens while the mower is also monitoring battery usage, motor load, wheel traction, cutting efficiency, slope angle, and obstacle detection simultaneously. Even the mowing pattern itself involves engineering trade-offs. Many lower-cost models still use semi-random movement patterns because repeated random coverage eventually cuts most lawns evenly over time. More advanced systems instead calculate optimized mowing paths that reduce overlap, save battery power, and shorten total mowing time. Then when battery levels drop, the mower switches into docking mode. Some follow the electromagnetic boundary wire back home. Others calculate direct return paths using stored maps and positional tracking. So while robotic lawnmowers may appear to wander randomly across the grass, many are actually performing constant electromagnetic sensing, positional estimation, sensor fusion, mapping, and autonomous navigation calculations every second they operate. If you like learning how everyday things work, please subscribe to this channel and like this video. Thanks for watching, and I hope to see you soon.